So the last lecture will be given by Tracy, who no longer needs introductions. So Tracy will be telling us about random walks on matrix.
Yeah, thank you very much. Also, thank you to Josephine for an excellent first 3 lectures in this series. So today I'm going to be talking about, the one sentence description is like, how did it come to be that 3 of the authors of this paper were computer scientists and not mathematicians? Like, why does anyone care about complete log concavity or Lorentzianity? I mean, one answer is it gives you like these nice inequalities on your coefficients. That's maybe why the mathematicians care. This is why the computer scientists care. So the motivating question is basically, given a matroid M, how can we, and because we are computer scientists, we say efficiently, by which we really mean like polynomial time, maybe quasi-polynomial if we're feeling bold, sample a basis of M approximately uniformly. We have some matroid M, and we want a basis of M. The reason this is a problem is like, in general, you can have exponentially many bases. So it's not like you can just like list them all out and then pick one. And the point is that like, using these tools I'm about to show you, you can get like arbitrarily close to a uniform distribution. So you decide that you're willing to have some level of tolerance, and then in like polynomial time in that tolerance, you can get close to the uniform distribution. So, spoiler alert, the answer is going to be a Markov chain. But maybe before I get into a more formal definition of a Markov chain, let's just like think about a graphic matroid. So, for example, M is a graphic matroid. So if you have taken an algorithms class, you may have seen Kruskal's algorithm, which basically gets you a spanning tree. If you haven't taken an algorithms class, it's just like you take edges, but you don't take any edges that make a cycle, and like theorem, this gets you a spanning tree. So it's easy to get one spanning tree. Right, in this case, our bases are exactly spanning trees. If I have one spanning tree, it's very easy to get to like a nearby spanning tree. I can do something where I like add any edge, theorem, this creates a unique cycle, and then I just remove any edge from this cycle and get a new spanning tree. So it's easy to get a quote unquote nearby spanning tree. And so you can think of this process, right, getting to nearby spanning trees as giving us some random walk on the space of spanning trees. And so the claims are twofold. First claim is that if I run this forever, I get the uniform distribution. So eventually you get, I guess, arbitrarily close to the uniform distribution. I feel like this is a step that a lot of papers kind of skip. They're just like, obviously, the stationary distribution is the uniform distribution. But I do plan to like actually show this today. And the second claim, which is what the computer scientists care about and where complete log concavity comes in, is that we get there fast. Where I will defer the definition of fast until a little later in the talk. So let's start with just a crash course on Markov chains. So this is a definition in quotes. A Markov chain is a memoryless random walk. So what this means is like, if I know where I am at a given time, it doesn't matter how I got there. Where I go next is independent of where I was before. So Markov chains come in all sorts of flavors. There are people in probability who just like study these things for their living. But we are going to specifically be talking about Markov chains with discrete states and discrete time. So we're going to have n states. And we're going to have discrete time. Just non-negative integers. And x of t is going to be our state at time t. And then we can represent our Markov chain as a n by n matrix, where our entries just tell us, like, if I am here, where am I likely to go next? So we get an n by n matrix P, where P j is the probability that x t plus 1 equals j, given that x of t. So if you think about how linear algebra works, if I have a probability distribution for where I am at time I, or time t, sorry, if I want my probability distribution for time t plus 1, you should convince yourself that this is just the same as doing right multiplication by p. So if the probability that x of t plus I is bi, then the probability distribution of x of t plus 1 is b transpose. And really, this is just like, you end up just like summing over all i's the probability that xt plus 1 equals I, given this, times the probability that we were at I to start with. And that should be exactly the probability that we end up with. So sort of by induction, if we want to take t steps, we just need to multiply by p t times. So if x of 0 equals I, probability of x of t is j is just ei times p to the t, take the j term. So another thing is sort of by how I set this up, if I sum across any row, I should get 1. Because that's just saying I'm like summing over all of the places I might go from I. And probabilities need to sum to 1. So we know that p times 1 is 1. But the left eigenvalues and the right eigenvalues of a matrix are the same. So there has to be some left eigenvector with eigenvalue 1. So this means there exists some pi such that pi times p is pi. And for linear algebra reasons, it turns out that this is going to have non-negative entries. I'd say this is not obvious, but it's true. And so this, appropriately normalized, is what we call the stationary distribution. Can you see if I write at the bottom of the board here? Okay. So pi. All right, so it has non-negative entries. So we're just going to normalize it so it sums to 1. So why is this important? It means that if I start with this probability distribution, I stay there forever. Like that is the sense in which it is stationary. It's like invariant undertaking more steps in my random walk. And so one more linear algebra fact. So all other eigenvalues of P have absolute value less than 1. This is like under some mild assumptions.
Can you write bigger?
Oh, yes. I forgot to say at the beginning, please let me know if you can't read anything. Stop me at any time for questions.
So we need to read the like line by induction.
Uh-huh.
Yeah, could you read it out?
Sorry, by induction. So if we know where we start at some state, if I want to know where I'm likely to end up t steps later, I just multiply EI times my matrix to the t. So basically if instead of taking one step in my Markov chain, I want to take t steps at a time, the transition matrix for that is just p to the t. And so what this means is that like the limit as t goes to infinity should just give me my stationary distribution. The point is like all of the other eigenvectors disappear. Because the eigenvalues of p to the t are just like the eigenvalues to the t. All of the rest of them are smaller than 1, so they go to 0. And so we're just left with pi. So yeah, this is a crash course on Markov chains. So before I define the actual Markov chain that we're going to look at for this lecture, like, are there questions on just like Markov chains in general? Yeah.
There be multiple, oh wait, sorry, actually you just answered this there, the other eigenvalue.
Yeah, so okay, so you can imagine like a random walk on a disconnected graph, for example. So one of the mild assumptions is that we shouldn't have a disconnected graph.
Right.
The other mild assumption is like if you imagine a random walk on like a bipartite graph, like we always know we're in the left half on even steps and the right half on odd steps. So the other mild assumption is that you shouldn't be a random walk on a bipartite graph. I mean, there's a more formal way to say that, but those are basically the two mild assumptions that we're putting on it.
So if you have only two bases, for example,
Mhm.
that would not work.
Well, we allow ourselves to stay where we are.
Okay.
So it's a self loops make us not bipartite.
Can I just, maybe just for the students, I think there are two graphs going on. You have this graph on the graph of matrix, and
Yeah.
you're also talking about random walk on a graph that is entirely different graph.
Yes, yeah. So the bipartite graph that I was talking about is like the vertices are bases. And they are connected if, you know, we do like a local move like this. But I'm about to define what these actual local moves are.
You're gonna draw a very toy small Markov chain for it.
Yeah, I am.
Okay, thanks.
Or at least part of one. Okay. So so this is like general Markov chain theory. Obviously, this is a much deeper mathematical object than I have just presented, but I want to just present the random walks that we are actually going. There's two different ones. There's the down-up random walk and the up-down random walk. You will see in a moment how they got their names. So we're gonna define, so let M be a matroid bases D. And I'm going to define the set of independent sets of M with a given size. I'm just gonna so remember that independent sets are just all the subsets of the bases. Just like we can there's like a set of axioms for when we have bases of matroid, there's also a set of axioms for when we have independent sets. So we're gonna define I and K to just be the independent sets I size K. And so we define the down-up random walk on our bases. So if we have x of t some basis, the first thing we're going to do is uniformly at random, I'm going to remove some I from our basis. And then second, we're going to get to like another nearby basis. So what I mean that is I'm going to add J, but we want to make sure that we do in fact end up at a basis. So such that B minus I union J is a basis, again, uniformly at random. But from now on, I may abbreviate as view A. So this gives us some random walk on our bases. If we are not at bases, but are instead at some smaller size of independent set, we can also define a up-down random walk, which is basically like, okay, here we started with something big, went small, got big again. Instead, we can start small, get big, and then get small again. So for K less than or equal to D minus 1, find up, down, random walk on IFT. What? Oh, bases B, rank D.
Oh.
Why I'm using D instead of R will become clear perhaps later.
Like second line, the x of t equals b equals.
Oh, sorry, that should be N.
Give.
Is this kind of relating to like when we said if we started with a spanning tree, you get to a nearby one? So
Mhm.
this one we have a basis and we can just like do the substitution to get a different one.
Yeah, so this isn't quite the same. So this would be, we start with a spanning tree, we remove an edge, and then we add an edge to reconnect. Here I was adding an edge, but
Okay.
we're spoiling the very end of the lecture, which is that this is the up or the down up random walk on the co-graphic matrix. So here we're going to start with x of t being some I of k, and then we are going to add some j such that I union j is an independent set one size larger. So this is why I needed k to not be d plus 1. Yeah.
Why can we actually ensure that we can always find such a j?
Here or
Like both ways? Like, why can we always add a j?
well, first of all, we can always add I back.
Oh,
But second of all, like this is basically basis exchange.
oh, right.
So as long as B isn't the only basis, we're good. And then here we're gonna remove some I. There. So somehow like if we do the up down random walk on like D minus 1. It's just like, so here you can picture the walk as going like literally up and down. And this would just be like, we cut off the first bit and do it up and down. So there was a request for an example. So let's look at the graphic matroid on our favorite kite graph. Graphic matroid. This guy. So let's say that we start. Let's say I start with this guy. So the yellow edges are the ones that are in my basis. The white edges are not. I might start omitting the white edges. And you can fill them in with the power of imagination. So, okay, step 1 is that I need to uniformly at random remove one of these edges. So with probability 1/3, I go to this guy. With probability 1/3, I go to this guy. And with probability 1/3, here we're missing like these and these and right, so here I'm not allowed to add this edge in. That is cycle, that is not a basis, but I can add either of these two, and I will do so with probability add. So half the time I go here, half the time I go here. The places I can go are either back to my claw graph or to this like zigzag guy. And then here, I can add any of these three. And I'm gonna do so each with probability 1/3. I can again either go back to my claw graph or to like this guy or to like, sorry, I'm kind of running out of room here. And then here, again, I can't add this one, but I can add either of these two. Probability 1/2. Can go back to my claw graph, or I can go to this instead. So if x of 0 equals this guy, then x of 1 might be one of the zigzags. It could be one of these like half rectangles. Or it could be the plugin. And these happen with probability 1/6. These are probability 1/9. And this is probability 4/9. Hopefully, if I did my math right, those should add up to 1. Questions up? Yeah.
So since I feel like this maybe makes intuitive sense, but I'm not sure if it's actually something that will be true in general.
Mhm.
Because we're kind of like taking this step away from the claw graph.
Mhm.
Is it always going to be that the original graph we had at step 0 is going to be one of our most likely options for step 1 because there's so many ways to get back to it? Or is that something that's only true in this kind of small case?
I think it should be true. I mean, it's certainly always one of the options, and that is important because that is one of the mild assumptions we need to get this convergence. I think it should be the most likely option, but I would need to think about it. A lot of times you also define random walks like this, where you're just like, with probability a half, I just always stay. And then with probability a half, I take a step. And that step may also be back to myself. So then it's like definitely the most likely option. Other questions?
I think I missed it, or I just couldn't see. Why did we, maybe it's like notation, I don't know, why x of 0 and x of 1? Why are you grouping them like that? You already said it.
Okay, so x of 0 is, I'm saying I start at the claw graph.
So that's when you get back to this.
And then x of 1 is like, what is the probability distribution after one step?
I see.
So like.
So there should be 3 more, 1, 2, 3, 4, 5, 3 more graphs, and those ones are 0, right?
Yeah, so I only ever like change one edge, so. Just something I'm about to talk about a little more. So yeah, you can think of this as being like one row of the transition matrix of this radical.
Well, I'm just saying there's 3 more graphs.
Yeah,
Those are 0.
There's some 0 entries, yeah. These are all good questions. Any other? Okay, so then I'm going to talk a little bit about claim 1, which is that we should get to the uniform distribution. One. Stationary distribution. Okay, I'm not trying to find this notation, but P down up makes the shape of a down up. It's uniform. So this means that like, if we run this Markov chain forever, we should get the uniform distribution. So that means like, this at least will eventually allow us to sample. And then like claim 2 is going to be that it lets us do it efficiently. So one thing that is true about all Markov chains, which I wrote over there somewhere, is that if we multiply on the right by 1, we get 1, like the all ones vector. So if we want to show that we multiply by left, on the left by the all ones vector and get the all ones vector, it's sufficient to just show that our matrix is symmetric. So it's P times 1 is 1. Suffices to show P is symmetric. Which means that PAB equals PBA for all bases A. So as Danya pointed out, like sometimes these entries are 0. And specifically, I claim that they are 0 when the two bases differ by like more than one element. So if the overlap between A and B is less than B minus 1, then we never go from A to B, because we can only change one element, and we never go from B to A, because again, we only change one element. So indeed, they are equal, and specifically they are equal to 0. So check. But like, okay, it's not everything is 0. We do have to go somewhere sometime. So if they share exactly D minus 1 elements, then we can write them as like S union I, and B is S union J. So S is going to be their intersection, I has one more thing, B has one more thing, and like because they are both sides D, what has to happen? So then let's think about like, okay, if I am at A, what is the only way I can get to B? So if I want to get to like this zigzag, for instance, from the claw graph, well, when I remove something, I must have removed this guy. Because otherwise, that left diagonal edge will be in my resulting tree. And then when I add something, I had to add this guy. So the only way in our down-up random walk to get from the claw to that zigzag is I first have to remove I, and then I have to add J. So the only way from A to B is I start at A, then I remove I, also known as S, and then I have to add J.
Can you explain again why, since you have equals one, it's enough to show this matrix is symmetric? Why is that?
Yeah, okay, so P times one, are we okay with P times one equals one?
It's saying one is the eigen.
Yeah, so this is like, when we sum across any row,
Yeah.
it says like, if I am at state I, where do I go? And the sum of those probabilities has to be one.
Mhm.
So that's just like,
How probability works.
yeah, that's how probability works,
Yeah.
exactly.
And then why is it?
So our stationary distribution is defined as like pi such that pi times p equals pi.
Uh-huh.
And so if p is symmetric,
What's pi?
pi is our stationary distribution.
What's the distribution?
What do you mean?
I'm sorry.
Okay, so okay, we know that one is an eigenvalue of any Markov chain matrix.
The distribution is like a vector.
It's a vector.
It's a vector on the, each state has a number and it's.
Exactly.
Okay,
Yeah.
sorry, I just,
Yeah.
okay.
So if P is symmetric, this means that one transpose P equals one transpose P transpose is P times one transpose. And this has to be one. If you have a symmetric matrix, your left and right eigenvectors are the same.
Okay. Okay.
Yeah. So let's think about. You're right, Patrick, this is very hard to move. Okay, so what's the probability that this happens? Well, here we remove something uniformly at random, so that happens with probability 1/d. And then here it's like uniformly among the things that we're allowed to add. So this is like 1/the number of k such that S union k is a basis. So like the probability that we go from A to B is like the product of these things. But similarly, if we want to go from B to A, we have to start at B. We have to remove J. And then we have to go up to A. And this again is probability 1/d. And now once we're at S, we're like equally likely to go to A versus B. So 1/, same thing. And so these are the same probability.
Sorry, could you like read out what is in the middle node of this like arrow thing?
Yeah, so this is A minus I,
Oh, it's
Which-
minus, okay.
which by definition is S. And this is B minus J, which is also S. So like, sort of the moral of the story is that once we go down to S, we forget that we came from A versus B, so we're equally likely to go out way, and like the probability from of going A to S and B to S. is the same. Did I see another question? Somewhere? No. Now is a good time for questions because I'm about to start talking about like fast mixing. Okay.
But, oh, how do we know the existence of eigen?
So we know that there is a left eigenvector. The left and right eigenvalues are the same. The fact that it is non-negative is from what's called the Perron-Frobenius theorem, which basically says if you have a non-negative matrix, your highest eigenvector has non-negative matrix.
I think I got my answer.
Okay. Okay. So my second claim, and where complete log concavity starts coming in, is that our Markov chain, or our down-up block, mixes quickly. So I promised that I would define what fast means. I will now do that for you. Right? If I want to prove something mixes quickly, I should say what it means to mix quickly. So the mixing time of a Markov chain P with stationary distribution time is T mix of epsilon. So epsilon is some, like this is a function. So I decide how well mixed I want to be, and then this tells me how long it takes to get there. So this is the maximum over all states of the minimum time such that if I start at state I and take t steps, then I am very, very close to my stationary distribution. So this is the one norm. This is just like the sum of the absolute values. When probabilists want to sound fancy, they call this, or I guess twice this, the total variation distance. But it's really just the one norm, I guess, up to scaling. So, right, what this is saying is like, my probability of being at a state is like very close to what it would be if I was fully mixed. And so there's a theorem. All right, Diaconis and Struck from the 90s that says, no, okay, under some conditions, which are basically the same conditions that we were talking about before, T mix epsilon is less than or equal 1/1 minus lambda star, and the second log 1/epsilon by star. So lambda star is the max of the second eigenvalue, the absolute value, the smallest eigenvalue, and pi star is the minimum entry of pi. So basically this is saying like, if in my stationary distribution, I only very, very, very rarely get to a certain state, it's gonna take me longer to mix because like I'm very unlikely to get there at any given time. Sort of intuition, but in our case, like our stationary distribution is uniform, so we don't really have to worry about that. In our case, it's also gonna turn out that lambda star is always lambda 2. So for us, T mix epsilon 1 minus 1 minus 1/1 minus lambda 2 log, so pi star is 1 over the number of bases. So this is the number of bases. of epsilon. So I'm not going to prove this theorem, but sort of the intuition is like, right, so the reason why we converge to our stationary distribution is because all of our eigenvalues, except for the top one, are like strictly less than 1. And somehow we're decaying exponentially, so the further we are from 1, the faster we should mix. So that's sort of where this like 1 minus lambda 2 is coming from, and then somehow like, the closer we want to get, the longer it's going to take. But apparently only logarithmic. Yeah.
So just to double check that I'm understanding the
Mhm.
mixing time definition correctly. The mixing time, like T, is like how many steps it takes for us to get within epsilon of the distribution we're trying to converge to.
Mhm. Where within epsilon is defined in some way, yeah. Yeah,
Can you, I just can't read, like, can you read off lambda star, pi star, and the, like, what's in the log?
in the log is 1 over epsilon pi star.
Okay.
Lambda star is the maximum of lambda 2 and the absolute value of lambda n.
Okay.
And pi star is the minimum pi I.
Thank you.
What's lambda two? What's lambda two? I know.
It's the second biggest eigenvalue. So our biggest eigenvalue is always 1.
Longer than.
What's our second? Yeah. And so sort of our goal should be to make sure lambda 2 isn't too big if we want to mix.
Lambda 2 is which eigenvalue?
It's the second biggest one. So the first biggest one is always 1. Second biggest one is lambda 2. Okay. So we are going to do a sidebar on simplicial complexes. So this sort of like Markov chains, like this is a very deep area of mathematics. People spend their entire career studying simplicial complexes, and I'm going to try to do it in like 5 minutes. So, Okay. So a simplicial complex is collection subsets such that it contains the empty set, so it's non-empty. And for all sets, the subsets of that set, we have, so it's like downward close. If you were in there, so are all of your subsets. So, for example, and this is really the only example I'm going to need, if M is a matroid, then the independent sets are a simplicial complex. So we call the elements of a simplicial complex simplices. I guess. So in fact, this will be pure of dimension u minus 1. So pure means the maximal simplices are the same size. And the dimension is just size minus 1. Why minus 1? Well, we want points to be 0-dimensional. It like makes the geometric intuition of dimension line up. So one thing to, okay, so if we have a sequential complex and some simplex tau, we need to find the link of tau. It's just going to be all of the simplices that contain tau, but then we remove tau. So you can think of this as like sort of the local picture around this simplex. Sigma tau. Sigma is the simplex, complex, and tau is a subset. So this is also a new simplicial complex.
You mean tau is a subset of sigma in the.
Oh, yes, thank you. So we take the simplices that contain tau, remove tau from them. Claim this is a simplicial complex. Should maybe check that, but yeah. So pop quiz. If delta is the independence complex of n, what is the link in delta of just, so okay, claim, let's assume that I is independent of not a loop. What is the link of I in this complex? In terms of matroids? I think it's, so we want I to be in the face and then remove I from it. So contraction.
Yeah, so it's contraction.
So this is same as M contract. So somehow like these independence complexes, I mean, first of all, they encode our matrix, obviously, but also like there are natural like people who don't do matroids also care about links of simplicial complexes, for example. So they encode these matroid operations in a pretty natural way. So the other way that we've been studying matroids is through their independent, or through their basis generating polynomials. So one thing to notice about simplicial complexes, so I define them to be like a collection of subsets that have this downward closed property. But you can sort of like, once we know the maximal simplices under inclusion, that exactly defines our simplicial complex. And we just take all the subsets. So we can translate this to polynomials. So if we have delta, a pure d minus 1 dimensional simplicial complex, we can just write down the generating polynomial of its maximal sum. Sum for tau and delta, the size of tau is d, because things with d elements are d minus 1 dimensional. Let me change these to CLS. So by this, I just mean the product of all of the xi for all I and z. So another pop quiz that I've sort of run out of room for. Okay. Here, question. If we have some simplex tau, what is, and I claim that these links are again simplicial complexes, so what is this polynomial for the link? So So I want to take all of the simplices that contain tau and then remove tau from them. What does that sound like on polynomials? Yeah.
Take the partial derivative. Expect like everything in town.
Mhm. So if I want the polynomial for the link, that's just the derivative with respect to everything in tau of my original. So I defined these down, up, and up, down walks on matroids. But I can define them on any simplicial complex. There wasn't anything special about being a matroid, right? I can start at a maximal simplex, remove something, get to another maximal simplex, or I can start at a non-maximal simplex, add something. Yeah, Tanya?
I was gonna ask that actually, so the first part of the proof was to show that we're tending towards uniform, and then the second part that we're gonna show is that it's fast, right?
Yeah.
So in the first part, we didn't really use, we could just use any pure simplicial, or like just
Mhm.
simplicial complex.
Mhm.
Awesome.
Yeah. It's so,
Let's talk about it later.
spoiler alert,
Yeah.
it's gonna end up being a property of these generated polynomials that makes it mix with. Yeah.
For this mixing fast theorem, you said something about the eigenvalues. Can you just say that part again? It seems important.
Yeah, so I guess so this is a theorem.
Yes.
You can just take this as a theorem. I mean, there's a proof written down that I'm not going to share with you. I was just trying to give intuition for why bounding lambda 2 feels like the right thing to do.
What
Yeah,
intuition
yeah,
again?
okay.
I didn't catch this.
Yeah, so the intuition is, right, so we're taking t steps. It's the same as doing like p to the t. And the eigenvalues of like a to the n are the eigenvalues of a all raised to the n. And so so I want to get close to pi, which is my eigenvector with eigenvalue 1, which means I want all of my other eigenvectors to decay to 0.
Okay, so lambda 2 is as small as possible is good for you.
Right, then it'll decay. Like the further lambda 2 is from 1, the faster it will decay.
And lambda 2 is positive or negative?
It turns out that actually I sort of glossed over this, it turns out our matrices are always like PSD or have non-negative real eigenvalues. So that's sort of hidden in this for us statement, but yeah, it turns out that lambda 2 is positive.
And the PSD part follows from.
Basically, like this down up random walk ends up looking like AA transpose. Like the down part is an A and A transpose is the up part. It's not obvious.
Okay, what about outside of matroid? What does positive definiteness come from?
I think in general it doesn't. In general, these things don't have to be PSD.
So it's the good local properties.
Mhm, yeah. Right. Oh, yes, sorry.
Is that a partial derivative taken there for the link with respect to tau?
Yeah, so this is shorthand for like dxi for all I and tau.
Oh, okay, thank you.
Like I think we saw this like partial alpha maybe yesterday,
Yeah,
and now we're using tau instead of alpha.
thank you.
Okay, so I only have 5 minutes left, but
Sorry.
that's okay. No, questions are good. This is good. I'd rather not finish everything and have people understand the part I did say than finish everything and have everyone be lost. Like more information is imparted the first way than the second way. Okay, so there is a very like a surprisingly deep, or maybe not surprising, there's a very deep theorem. I looked up last night. The proof of this thing is like 50 pages. So definitely not going to prove it. So we have delta pure E minus 1 dimensional complex with 2 conditions. So one is that the one-dimensional simplices of all of the links form a connected graph. whenever tau has size at most d minus 2. Second is that whenever the size is exactly d minus 2, the up-down walk on the link has lambda 2 less than. So once we take size d minus 2 link, we're left with just a graph. So the up-down walk is just like we start at a vertex, move randomly to a neighbor, and then iterate. So we got like vertex to an edge, and then pick an endpoint of the edge and do a random walking. And then the conclusion is that the second eigenvalue of the down-up walk, so this is now on the maximal simplices, is at most 1 minus 1 over. So I guess sort of the moral of this story is if we have a simplicial complex that's like pretty well connected, and this is stronger than just being connected as a simplicial complex, right? This is a very strong connectivity assumption. And if we look at like any little neighborhood, we mix very well there. And we still mix pretty well all the way upstairs. So was there a question?
Sorry, I just couldn't read, but you said it, so.
Okay, yeah. So with the last approximately 2 minutes I have, okay. So let's start here. So if we look at the one-dimensional simplices of the link of tau, right, this is d tau of f. And then the edges here are exactly the, so this has edges, ij, such that tau union ij is in our simplicial complex. And so these are exactly the edges that show up from the lecture yesterday when we were talking about indecomposability. Right, that's saying that ij share a monomial in this polynomial. So one is saying that d tau f is indecomposable. And then here, now I'm taking d tau f, where the size of tau is d minus 2. And so this is the part that I was, but like, basically the up-down walk on, so claim that I think I have run out of time to prove, is that the up-down walk on this link of tau is some positive diagonal matrix times the Hessian of this polynomial. This is a claim. It's honestly, it could be an exercise. And so the point is, if this guy has lambda 2 less than or equal to 0, which was the second condition for being completely log-concave, then this guy will too. And it's actually if and only. So lambda 2, the up down of tau is less than or equal to 0, if and only if lambda 2 is the Hessian of d tau f. So the punchline is that the conditions for this theorem that implies fast mixing, right? So this is like bounding lambda 2 away from 1. And the theorem, or the punchline is that like these conditions for that bound are exactly the same as this generating polynomial being completely null. I think I am out of time. Are there any questions?
Well, what does it say? Has lambda 2 less than or equal to 60?
This guy?
Above in white, yeah, has lambda 2, I just can't see it.
It's, so for all tau of size d minus 2, the up-down walk on the link has like, right, this is now a new Markov chain. And so we can talk about the eigenvalues of that guy. And what we want is that the second eigenvalue is less than or equal to 0.
What is that letter above P2, claim P2 lambda n?
Oh, this is for up-down. Right, down up was a V, and so up down is a upside down V, yeah. So I don't think I defined that notation earlier when I was supposed to. Yeah, Donnie?
When we were getting like to the finale,
Uh-huh.
I was excited for us to like choose a particular tau or size of tau. But you left it general. I don't know if like, do you have anything to say about that? It feels stronger and like better. Tau is general. So far, we've only been taking like one step, you know what I mean?
Yeah.
But now in this proof, we've left tau to be general, so like, do you have to leave, or like, I don't know what,
Yeah, so
about that?
So this theorem says like all of the links are indecomposable and all of the like very small links mix fast.
But I'm saying I'm impressed, maybe, I don't know, maybe it's just a comment, not really a question, because to apply the theorem to the thing that we're trying to prove, I thought you were gonna select a special tau, but you didn't have to do that, so I don't know.
Yeah, so this theorem says like our very small, all of our very small links mix fast. And then the 50-page proof shows that our big block also is gonna mix fast. So like I think, yeah, somehow this already feels like pretty surprising that only looking at local pictures like this tells us something about the global picture. So like, if we just have one link that mixes fast, like maybe the rest of our simplicial complex is like real bad and there's no hope of getting any sort of fast. Yeah, Dachi?
Here you said lambda 2 is positive or like not negative. There it's like negative.
So here, these are like the very small random walks.
What is it?
So these are up-down random walks, like literally on a graph. Whereas there, that's this P down up. Right, so what we want is to sample a basis.
Yes.
Right? And so for that, we're gonna do this down up random walk. We start at one basis, we do down up, get a new nearby basis, run this for ideally polynomial time. And so there we want to bound the mixing time of that guy. We want to bound lambda 2 of that big walk. And what this is saying is that if we can bound the eigenvalues of a bunch of small walks, then that gives us a bound on the big walk. So like here, these are like non-positive, and here this is just like it's a constant away from 1. So like there's a pretty big gap between the lambda 2s, which is maybe why this is like a surprising result.
What's this? Sorry. Maybe other people can ask. Ask later.
I think maybe I'm not understanding your
I
question.
don't understand what a small walk is.
Okay, so when I look at like link of tau, it like literally is a graph.
Oh, I see.
Something. Right, and I do a walk where it's like I start at a vertex, and then I either stay at the vertex or randomly choose a neighbor to go to. So like I'm here, I might stay here, I might go here, I might go here. Right, so this is the up-down walk, is I'm gonna pick an edge, and then I'm gonna pick one of the vertices on that edge. And that I want that to have non-positive second item.
So is this some like local global principle?
It's exactly a local global.
Can you say again how the yellow claim links to theorem from yesterday?
Right, so the yellow claim just says that like, if I want to write down the transition matrix of this up-down walk, it is up to scaling by some diagonal matrix. That's basically gonna be like making the rows add to 1. That's really what we're doing. It's exactly the Hessian of the, like this partial derivative. And then by some linear algebra tricks, some of which were on the problem session yesterday, like that means that this thing has non-positive second eigenvalue if and only if this thing does. I guess this thing having non-positive second eigenvalue was exactly this complete log-concave.
Seems like for most of the talk, we've been dealing with down up
Mhm.
random walks, and then here suddenly there's some result of that up down random walks that suddenly implies something
Mhm.
about a down up random walk. Like, why, like, how did this happen?
So, okay, I sort of glossed over this. So let's think about the down-up random walk on bases and the up-down random walk on like rank -1 independent sets. Somehow these are like, to abuse this word, possibly like morally the same random walk. It's just whether we start at an up step or start at a down step. And to make the morals more concrete, they are going to have the same non-zero eigenvalues. And so like in this 50-page proof, you basically like go up and up the chain until eventually you get to like the up down on codimension 1 simplices, and that gives you the same thing for the down up. Yeah, Lizzie?
So does, I wanted to prove something as Lorentzian, is this easier to prove?
No, this is definitely harder to prove.
Okay, cool.
Yeah.
So at this part of the end, you mentioned that we passed like from considering matrix to like more general simplicial complexes. Is there any result, or do you know anything about like a characterization for which types of simplicial complex you can like just satisfy this?
Well, okay.
Bigger than just matroids or
So this Kaufman-Oppenheim result, this is actually a special case of it.
I see.
You can bound different size links and not just by 0 and get some stuff. But like, so, right, I guess proof is a strong word. I tried to justify that like these two conditions in this special case are exactly the same as complete log-concave. And based on other things Josephina said, like somehow completely log-concave, like square-free polynomials are basically matrix.
I think this is maybe repeating the question, but I wanted to
Uh-huh.
check again. So in the Diaconis Stroop, we have lambda 2, which is happening for our overall graph, and then here, and that lambda 2 is positive or non-negative.
Mhm.
And then here in the link, we want the lambda 2 to become negative, and is that correct?
So I think this is also sort of a difference between up down and down up,
Okay,
I think. But I guess somehow here, like, because we're so small, like maybe it's more reasonable to hope that
but the difference in situation is like, that's much more global, and this one is like our local lambda 2 that we're looking at.
yes, so the Diaconis and Strict thing is just like a fact about Markov chains.
Okay.
And then this is like a condition that we can check on one very small Markov chain.
All right, well, I think we've had a lot of great questions. We can continue over the coffee. Let's thank Tracy.